Jörg, for the kind introduction, and thanks to all organizers for inviting me. So it goes without saying that I would have preferred to deliver this talk in person, but this is probably the next best thing. So yeah, I'm going to talk about the dynamics in dipole and higher moment conserving systems. And in fact, I'm going to talk or going to summarize a number of different projects done with several collaborators, including a large number of current and former students, like Giuseppe, Julius, Johannes, Tibor, and Pablo. Tibor and Pablo were really the main driving force behind many of the projects, and they are both in the audience, and Ruben Brezen, and also with my colleague in Munich, Michael Knapp, and Monika Eidelsburger. So when thinking about many-body systems out of equilibrium, we often think about systems which are fully ergodic, systems which are thermalized, which are described by few conserved quantities in the long time limit, where observables relax to thermal values and all eigenstates are thermal. And often we contrast this with many-body localized systems, systems that do not thermalize, systems which are described by an extensively many integrals of motion, where we do have an infinite memory of the initial states and where none of the eigenstates are thermal. And in between, and this is what receives quite some attention recently, are now systems that have some intermediate behavior where part of the eigenstates thermalize while others in the middle of a spectrum are non-thermal. And two examples that I'm showing here are gauge theories and also systems with many-body scars, right? I mean, systems where for certain initial states, the systems seem not to thermalize. And in this context, systems that obey both or a combination of charge and dipole conservation show some quite interesting properties, which I mainly want to discuss in this talk. And let me first illustrate the idea behind it. So we take a system where we have a U1 charge conservation. So we have some charge conservation of charge Q, and we also conserve the associate dipole moment, for example, P. And this is how it looks for example, for a spin 1 model. Now, this has been shown a couple of years ago in works by Fractal, that the combination of these two symmetries puts constraints onto the mobility of excitations, forming so-called fractal excitations. To illustrate this idea, let us, for example, start from a simple state where all states are in the SC equals to 0 eigenstate. And now we create an excitation by acting on that state with the S plus operator. So now with this, we created a configuration that has the total charge Q equals to 1 and the associated dipole moment is 0. Now, this isolated charge is completely immobile because the moment that we would move the charge, we would change the dipole. So the only way for the charge to move is that it has to create or it has to emit a dipole excitation, which then by itself can move freely. But for the charge to move again, it would have to emit another dipole in order to conserve both Q and P. So then this raises interesting questions about how these kind of conservations, or like how the combination of these conservation laws changes the kind of local unitary dynamics. And it was shown in a work by Pai and others that certain systems having these symmetries actually fail to thermalize. And the question is like how robust this actually is and how this can be generalized, etc. And this is exactly what I want to talk about. And in fact, what I'm going to do is I basically just give a summary about different works, those different works listed here. So I first discuss the idea of so-called Hilbert space fragmentation and fractal dynamics in one-dimensional systems. And in the second part, I want to show some ideas, and this is a collaboration with a group of Monika, how these kind of relevant models can be experimentally realized and how this kind of fragmentation can be detected experimentally. And the last part, I want to talk about some ongoing work on generalizations to dimensions larger than 1. So please feel free to interrupt me whenever any questions come up. Good. So now we want to look at a specific model that has the conservation of both charge and dipole, and we look at a specific model Hamiltonian here, which is a spin 1 Hamiltonian containing these kind of 3 spin terms. So we have s plus, s minus squared, s plus, and these terms now clearly conserve both charge conservation and dipole conservation. And now we can take this Hamiltonian and we calculate with respect to this Hamiltonian the infinite temperature autocorrelation function between SC and SC. And this is plotted here in a semi-log plot. And what we notice is that pretty much independent of system size, that this autocorrelation function do not go to the thermal value. So this system does not thermalize. If, however, we extend this Hamiltonian by adding to it the term H4, which again conserves both the total charge and the associated momentum, we see that the picture is different, but instead, after a sufficiently long time, the autocorrelation function reacts to the thermal value, so it goes to 0. And well, in this work that's shown below, we investigated this in quite some detail by identifying different kind of frozen states, and also we basically can show how basically the Hilbert space is fragmented into different sectors. So basically, we do have some sort of non-local kind of conserved quantities, which lead basically to a fragmentation of the Hilbert space. And the upshot is that we can then distinguish between different types of fragmentations. So in particular, in the case, if we have, for example, only H3 in the case before, we have what we call a strong fragmentation. In this case, we find that a given symmetry sector described by a total charge Q and a dipole moment P decays into an exponential number of sectors, exponential in the system size. And in this case, the largest sector scales actually slower than the total Hilbert space dimension, right? So the total Hilbert space dimension for a spin 1 system scales as 3 to the n, while in this case, the largest sector can be described by an effective spin 1/2 model, in fact. And this is in contrast to what we would call a weak fragmentation, where we also can construct an exponential number of sectors. However, the largest sector in this, scales as 3 to the power of n. So basically, in the thermodynamic limit, the largest sector dominates the entire system. So and this explains why the system here on the left doesn't thermalize for any initial states, while in the right-hand side, this is more reminiscent of what we would call scarce states, because if we choose a specific initial state that would lie in one of these small sectors, we would observe a non-thermal behavior. Now, what we then looked at is the kind of universal behavior for charge transport in the weakly fragmented regime, right? So because in the weakly, if we just look at the autocorrelation function time between charge and charge, we found that it does go to 0. The question, how does it go to 0? And it can't really obey regular diffusion, because regular diffusion processes would involve processes that, for example, violate the dipole conservation. Right? So this we can see easily, for example, by melting a domain wall, then the charges leaking to the empty part would violate dipole conservation. So we then derived, and this is done in the work shown here at the bottom, we derive the general hydrodynamics under the assumption that the mth moment of our conserved quantity is conserved, right? So in this case, it would be the mth moment of SZ. And what we then derive is that the autocorrelation functions decay as t to the minus 1 over 2 times m plus 1. Right? So we see that this behaves, so the charges diffuse obeys subdiffusion. And we then compare this to numerical simulation, and we just show here 2 tests. So the first test, and this is the one shown on the left, is where we do not compare to a unitary dynamics, but instead we are looking at the dynamics of a classical cellular automata, right? So each of these blocks is now shuffling around the charges in such a way that we conserve both the charge and up to the mth moment. And we plot here in a log-log plot the autocorrelation function. And what we see here is that indeed, for a system with only dipole conservation, we find the expected t to the minus 1 over 4 scaling. And for a system that also conserves quadrupoles for m equals to 2, we find a t to the minus 1 over 6. And we also compare to some exact diagonalization dynamics where we consider a Hamiltonian that obeys, in this case, a dipole conservation. And we see that the results are at least compatible with the expected t to the minus 1 over 4 scaling. Good. So this is all I wanted to talk about regarding the Hilbert space fragmentation, basically the distinction between weak and strong fragmentation, and the fact that we do find universal transport behavior. So we find subdiffusion with specific exponents in the weakly fragmented regime. Now let me switch gears and talk a little bit about ideas how to realize this kind of physics in experiments. And the experimental setup that we're looking at is relatively, at least conceptually, relatively simple. So we are looking at a Fermi-Hubbard model with nearest neighbor hopping in a linear potential, as illustrated here. So particles can hop between nearest neighbors, and the particles have a linearly increasing chemical potential, and we have the Hubbard interactions. So if we take the system without interactions, this would be the particles would be Wannier-Stark localized. And in fact, a similar model was looked at before in different works, including U and additional perturbations, for example, weak disorder or a harmonic perturbation. And in those cases, this model would exhibit so-called start many-body localization. So it would be a localized system. However, now what we have in mind is a perfectly linear potential with no perturbations. And this model can, in a very good approximation, be realized in the experiments, which is shown here by comparing the experimental data in terms of these dots with DMIG data on these solid lines. Now, what's interesting is that if we now take this Fermi-Hubbard model, including U and including a finite interaction, then we can perturbatively distinguish different regimes. So one regime, for example, is where U is a small perturbation and the delta is large compared to the hopping, right? So in this case, we would find that to lowest order, the perturbation would be dipole conserving kind of squeezing terms where just one particle is hopping up, another particle is hopping down. And these processes are exactly of the type that we are looking at before, right? So these would be exactly the terms that conserve charge and its associated dipole. But then as we tune the ratio of U over delta, we find other regimes. So we find sort of resonant regimes when, for example, U is of the order of 2 delta or 4 delta, etc. then we get different types of kind of perturbatively derived dynamics that can be kind of more ergodic than the very constraining dipole one. And the way that we just plot it here is that we just look at the return probability as function of delta and u, and we see here these regimes where the color is lighter, and this is where we have certain resonances. Right, so basically the upshot is that as we tune the parameters in this fairly simple model, we can reach different regimes where at least the kind of intermediate time regime is then described by effective Hamiltonians of different types of constrained hoppings, right? So it can be pair hopping, it can be the squeezing and the like. So with this, we can now compare basically the main ideas from this Hilbert space fragmentation to the experimental data. And here basically all I want to show from this plot is that when looking at the imbalance, like the imbalance between the charges on even and odd side, I mean this is like a quench starting from a charge density wave of singlons. We see here the difference between the non-interacting regime where it's Barnier-Stark localized and the case where we have these additional processes leading to a lowering of the imbalance. And we can now specifically look at a certain regime where we have these specific squeezing terms, and we can now compare up to sort of relatively long times, up to here sort of 100 or so tunneling times, and we can compare the effective models, these are the solid lines, to the experiments as shown here as these dots. And we see at least there's a fairly good quantitative agreement between the predictions of the effective model for the different doublon sectors and the actual experimental data. And this is hinting at the fact that the, at least to lowest order, that these simple effective model that exhibit these Hilbert space fragmentation do describe these experiments. Good, let me now for the remaining very few minutes just mention some work in progress, namely that we are now thinking about extending the same ideas to higher dimensions. And to start, we look at a model that conserves the total charge, the associated dipole, and a certain quadrupole terms, the ones listed here. And a simple, rather local Hamiltonian that has these conserved quantities is the one shown here. So in particular, we take these 3x3 plaquettes, and we have now similar to the squeezing term that we had before, where particles hop inside, or where we have like S plus, S minus squared, S plus. We have here now a term where we have S, say S plus on the red bonds here, and we have S minus for S minus to the power 4 in the middle. And this term is chosen because it does in particular only have these kind of symmetries and not additional accidental sublattice symmetries and the like. So now we can take this kind of Hamiltonian, and we just can perform a study similar to what we did for the one-dimensional system. And here in this plot on the left-hand side, we plot the so-called frozen site density, which is a proxy for having this Hilbert space versus strong fragmentation. I'm hitting the 20-minute.
Well, that's, yeah.
I'm
20
done
minutes.
in a few moments.
Okay, great.
Good. So then what we basically show in the left-hand side, we're using a frozen site density as introduced by Morningstar and others to indicate Hilbert space fragmentation. And we see here basically as we now tune the local spin, that for spin 2, we find that the system appears strongly fragmented, and for S larger than 2, it is weakly fragmented, and we see that the frozen site density goes to 0, and a similar behavior we also see in the autocorrelation function. And again, in analogy to what we did in 1D, we can basically exploit the extra constraints that we get due to these symmetries and write down hydrodynamic equations that then correctly predict the long time relaxation of the charge correlations. And lastly, let me just briefly mention it, and this is something that we found quite funny or interesting, is that if we take different types of Hamiltonians, like for example, the one as shown here, where we just extend the system to have now S plus on the outer, like the red bonds and like the red sides, and S minus on the blue sides. In this case, we have additional symmetries, and those become very nicely visible when we just look at the Fourier transform of the correlation functions. So we find the moments, including charge, dipole, etc., here in the center. So this is this dot that's showing up here. And here on the these straight lines, these are the subsystem symmetries of a system of charge conservation, or like a modulated charge conservation on straight lines. But then we have also additional symmetries here that show up as the different commensurate and incommensurate momenta. And we are still trying to figure out what this means for the hydrodynamic description. So let me now conclude and mainly thank my collaborators on these projects again, and thank you for your attention.
Yes, so thanks, Frank. Are there questions? Sebastian, or who has a first question? Unmute yourself and ask the question.
So I have a question. This is Caden. Thanks for the great talk, Frank. So this notion of strong fragmentation, where ETH fails, why do we distinguish this from MBL? What are the key characteristics that are different in these two scenarios?
Well, I mean, to start, I mean, we don't have necessarily local integrals of motion, right? So the sectors can still be quite extended. I mean, that is a significant difference between the discrete fragmentation and MBL. And moreover, we can still have volume law and entanglement in those sectors, even though they don't grow with the full size of the Hilbert space.
Okay, some more questions, Sebastian Divya.
Yeah, so I was wondering, I mean, it may be just a false friend by the name, but there's also these glass models for glass forming materials, which are also spin models with these kind of local constraints. Mm-hmm. They're even called kinetic constraints. I'm not sure if you're aware of any connection that may exist.
Oh, there are a bunch of connections. There are several connections to these models. I mean, also these kind of cellular automata models that we're using basically to get these kind of universal properties. I mean, these are exactly the type of models that are also used in that context.
Ah, okay, so you're saying for all of these models, the one could look for these kind of dipole charges that are conserved, or? Right.
You know, this is also an important point. I mean, the type of scars, or like the conserved, like this is basically all classical, right? So as I shown here, for example, while initially we were motivated by these quantum systems, the key features also show up in a simple model of these automata. There's a nice work by I should have the authors who were on. But anyway, there's basically a distinction between these kind of classical models, and there's also a quantum scar version of this. But in this case, all I talked about here is in this case, in this sense, classical.
Thank you.
Okay, thank you. Is there more questions? So maybe I would ask you, you had some, showed some first experiments from Monica in Munich. So what would be the, your dream to show that, you know, some of these things are important, or show where they break down? Do you have any?
I mean, what I would
specific?
like, I mean, well, with this model here, for example, we do have a case where we just compare a model of like a specific model, like a specific parameter regime, and we can compare the experimental results to the numerics done for the effective model. But I mean, what I would think would be really cool is that, for example, by Vedika Kemani and others, they proposed a transition, right? So there's basically you just choose a specific dynamics, and as you tune the dynamic, as you tune the filling, you can actually tune a phase transition between a strongly to a weakly fragmented regime. I mean, seeing this in experiment would be really nice, right? So if we just basically have the same perturbative dynamics, but we would just change the filling, we would see this transition. So that could be a very nice thing to do.
Yeah. So one quick question to this diagram. So the blue one, why does it, you know, drop so fast? And it's this, is this some? Do you have any idea what's happening there? That it basically goes immediately. It looks like that it immediately goes to the, you know, very close to the final value compared to.
Right. I mean, the idea is probably easiest to understand in this picture here, right? So let us say that we start from an initial state which actually lies in a small sector. What's going to happen is that within this sector it thermalizes fairly quickly, but then it's going to be stuck here. And if this kind of Hamiltonian, the exact Hamiltonian, would be stuck here forever. For this model, like for this kind of perturbative generation of this model, eventually it would further drop, because eventually the system would spread over the entire system. Now, if we start from another block, which is a larger block, then it would again quickly thermalize within this block. And this is probably what I should point at, right? So depending on if we start in this block, it would quickly thermalize, but be stuck far up because it's a very small block. But if you just initiate it here, it would again thermalize quickly within this block, but then just be stuck at some non-thermal value.
Okay. So there was another question by Zala.
Yeah, hey, so kind of related. So how robust is these two perturbations that break the symmetry? I mean, is it usual kind of perturbation square type of perturbation theory, or can you have some special effects because of the structure of which blocks you connect?
No, there is, I mean, like we just did some numerical tests with it, and it appears like the moment that we break these symmetries, it just goes to zero with what we would naively expect. So there's no, I mean, we haven't at least found a model where there would be any pre-thermalization, etc. So it's basically just the moment that we break these symmetries, the whole thing is gone. In this sense, this kind of physics is really fine-tuned.
Mm-hmm. Okay, thanks.
But if I can add to that, I mean, in the models where you do have the tilts, there you do get some kind of pre-thermalization, because the tilts do have a discrete spectrum. So this is there
right.
in the version of the. So Rahul and I also have simultaneous work on this, and this is discussed in that section there.
Yeah, but still, I mean, if we just take these models and we would just like this model by hand, if we just add like a term that violates dipolar conservation, then it would be gone. Right?
Sure. But if you get the dipole conservation already in a pre-thermal sense by adding a large tilt, then you can add all sorts of other stuff.
Because then we get this energetic term that basically enforces it.
Right.
Okay. If there are no more very urgent questions, then let's thank Frank again for the nice and beautiful talk. And the next,